good morning, geometry friends. Jesus, Jesus, and more Jesus. We are here on our last section of chapter 9. We are so close to being done. 9.6, geometric probability. So for all you risk takers, gamblers out there, insurance salesmen, we're going to be talking about probability and how it relates to geometry. What gets better than that? And so we've got our definitions and our questions here for, again, homework 9.6. There's 3 definitions, and so I've already gone ahead and defined those because I didn't think it'd be that interesting to watch me write them out, but we'll review them first. The first is geometric probability. Okay, so probability was actually something I didn't enjoy very much in high school. Always felt kind of confused by it, but I'm going to try to make it as simple as possible. In that, probability is simply a fraction. It's a fraction of something over something, and it's the amount of outcomes. So it's the amount of something that something takes place over the amount of possible outcomes. So in other words, the probability of something happening is the amount of things that could happen and the amount of things you're actually measuring that might happen. And so the book, just to jump down, gives us, you're going to be doing 3 examples because in geometry, this has to do with area or length, the number of like a selected space over the number of possible spaces. A very typical example is like a dartboard where you have different regions, and to find the probability of hitting a certain part on like a dartboard would be the area of the selected area over the possible area you could hit. And so you see that in 3 representations here. One is a number line where you could calculate the probability of hitting certain sections of this line with this fraction of, say, the probability of hitting AB, that would be then the outcome over, well, what's possible to hit? Well, that would be the entire area of A to D. And so we're going to go over that in question 1, but you could calculate it with the possible pieces over the total pieces here, or with an angle measurement here, where you could calculate the probability of hitting this piece on this circle, or receiving this piece on this circle, or however you want to do it. Again, with the actual over the possible area. And same thing here, where this is going to be with angle measures, and then this is going to be with general area, that you can calculate a geometric probability of hitting this shaded region by finding the actual area of what you're trying to hit over the possible area of the entire thing. And so it's a fraction of, again, what you're looking for over what is out there, and another way to think of it. Okay, and so kind of the 2 terms that you just want to be clear on is sample space and event. Sample space is the larger total space. So this is let's go ahead and add it. This is the denominator, because this is what is possible. This entire circle is your sample space. This entire rectangle is your sample space. A to D would be your sample space, because those are the possible areas that you could be hitting. Whereas the event is the numerator, the top, and that is the number of actual outcomes. And so that would be this shaded wedge here, this shaded triangle here, or whatever I selected for this number line. If I say the chances of hitting BC, then that becomes the event, or B to D, then that becomes the event. So this is the numerator. And so another way to finally write the geometric probability would be the event over the sample space. So that's the same way of rewriting what is also being said in the first definition of geometric probability. That your probability is your event over your sample space. Okay? And so we're going to talk about all 3 of these examples specifically here in question number 1, and then we'll practice them going through the other 3 questions. Okay? Okay. So number 1 says, how do you calculate geometric probability for length, angle measure, and area? And those are our 3 examples here: length, angle measure, and area. And so it's fairly easy. Your probability we'll start with length. Length would simply be the selected length over the total length. selected length over the total length. So, for example, looking at this line, say I want to find the probability of hitting, I'll just BC, keep it simple, BC. So then that's the selected length. So BC would be over then the total length of AD. And I would divide that. And anyway, that's the answer without specific numbers. Or if there were numbers there, if we knew this was 3 and the total length was like 7, then we would go ahead and divide those. And then we'd get a decimal that would be our percentage. Or we'd get a fraction that would be our percentage that represents our probability. Because probability could be like, a 30% probability, or it could be a 1 out of 3 probability. And so it's always going to be a fraction. And fractions can easily become percents, as you'll see. So length, again, you just pick the selected length. If I change my selected length to AC, then it would just be AC over AD. Okay? For area, I'm sorry, actually we're going to do, we'll do it. I'll do them out of order since I already wrote it. Area, that's just simply the area of the shaded region, assuming that's what's selected, over the total area. Okay, so for this specific example, it would simply be the triangle area, and so you'd calculate that, divided by the entire rectangle area. Now, I'm just taking this from the chart on page 630. That's where we're copying this down from. So, again, the selected area over the possible area. And notice in the possible area on the bottom, it's the entire thing. You don't subtract. It's not like the shaded region versus the white region. Don't get confused there. Because when you're of all possible outcomes, you got to take into account everything as possible, and then here's what you're actually trying to hit. So it's much easier that way. But so this is total triangle area rectangle area with the triangle area on top. And then going back to angle measure. Yeah, and you can see the pattern. It's pretty straightforward. Skip ahead if this is boring. That then the angle measure would be the same thing. You'd have the area of the, the selected degrees. It's pretty easy here. We don't have to use the area. Selected degrees over, I'm going to write it two different ways, total degrees. So these problems I think are really simple. Because they'll tell you the angle measurement of this and say, oh, this is 60 degrees, the wedge. And then they'll say, put it over the total degrees. Now we can go ahead and simplify this because these are always going to be done with circles on these angle measurements, and the total degrees is fixed because how many degrees have to be in the circle? 360 degrees. So I'm going to go. This will always be 360. And so the angle measurements will be real nice because they'll ask you for this region, or they'll give you this angle measurement, and then you'll just divide that by 360, and then that's going to go ahead and be your probability of hitting that shaded region. Okay? So in all three cases, you're taking the selected piece or the shaded piece, and you're putting it over the total length, the total area, or the total degrees. Okay, let's look at some actual examples. Number 2 says a stoplight. Now, I specifically gave number 2 because it's kind of a tricky example for the number line. The most basic number line is simply they give you number measurements and you can calculate the selected length over the total length. We're going to do the stoplight one because that kind of shows how a number line can be created from a word problem. It says a stoplight has a cycle of green for 25 seconds, yellow for 5 seconds, and red for 30. What is the probability that the light will be yellow? Now, you don't have to use a number line here, but I'm just going to demonstrate how the book does, and this is just example number 2. But you could imagine you have this duration of a stoplight, and you could imagine it as a number line. And so first of all, you have 25 seconds for green. Let's put a big G. Then you have 5 seconds of yellow. And then you have 30 seconds of red. Bummer. Our lights around here are much better than those in LA, so we should be thankful. Okay, so we can look at that time breakup of 25, 5, and 30 seconds as distances. I guess you're probably with these little dots. Distances on a number line, and then we can calculate the probabilities thinking of them as lengths. You probably could have done this without the number line, but here's how the book does it. So what's the probability of the light being yellow when we show up? Well, what is the selected length? So yellow has a time of 5 seconds. So that is my selected time. It's going to be, there's a period of 5 seconds where it's yellow and that I'm looking for. What is the total time of the cycle of the light? Or what is the total length of this line I've created? Well, 25 plus 5 is 30. 30 plus 30 is 60. So I have 5 possible seconds to be yellow out of a total of 60 seconds possible within the cycle. And so there's my fraction. And then you can reduce that fraction. That fraction reduces to, so out of 1 out of 12 times, I'm going to hit that yellow light. Or if I go ahead and just calculate it here, 1 divided by 12, or I'm going to have a 0.08 0.08 chance of hitting the light at a yellow. Notice this very easily, if you move the decimal place 2 places, this basically means you have an 8% chance. So that means you have a 92% chance of hitting red or green and an 8% chance of hitting it when it's yellow. And sometimes the answer is expressed as a fraction, 1 out of 12 reduced. Sometimes they'll put it as a decimal. I'll usually be turning it into a percent because to me that makes the most sense when we talk about probability. I mean 1 out of 12 too. That means 1 out of 12 times you arrive at the light, it will be yellow. The other 11 times it's going to be green, or the alternatives, green or red. Okay? So then there's a second part to this question, which is what about not red? What about not red? So if you show up to the light, what's the probability that it will not be red? Well, so then we look at, so what section of the line represents not red? Well, green and yellow. So the selected region in this case is 25 and 5, because either of those times it's not red. So that's 30. Again, out of the total possible, which is still 60, because I'm doing with the same line cycle. So that's 30 out of 60. So we can reduce that. That's 1 out of 2. So that means 1 out of 2 times you arrive at the light, it's not going to be red. A decimal, that's 0.5, which means that the percentage, you have a 50% chance of hitting the light when it's not red. 1 out of 2 chance. Okay? So that's as an example of how you would do this with the lengths or with number lines, and how you'll get problems based on time, and we'll do one of these on the classwork where you can express them as a line. Okay? Selected over possible. Selected over possible. And sometimes you can see that will involve adding sections together. Okay, let's look at the other 2 examples. We're going to have it. Number 3 is angle measurements. Number 4 is area. So number 3 says we're using the spinner. So you're using example number 3 on this, and I went ahead and drew it here. And it says, what's the probability the spinner lands on purple? So purple's this box here with 75 degrees. So this is really simple. My selected probability is purple's somebody's favorite color, so that's just 75 degrees over how many total degrees in a circle. This will always be the same, 360. So there she is. That's my fraction. I can reduce that if I want to, but there's no reason to. We can just do 75 divided by 360. So we get, let's see if we like this. Yeah, 20.21. 0.21 as our decimal. You can reduce that fraction if you want to. I'm not going to. Which is then 21%. So you've got a 21%, or a little better than 1 in 5 chance of hitting this zone here. So 21. I should probably box these. Okay? 21%. Again, actual over possible. And then it says, second version of this is what's the probability it'll land on purple and yellow. So now we're increasing the numerator. We're increasing the event. So now we're adding in this. So now it's not 75, but now it is these two together, which is 175 over 360. And so then it's the exact same process. So notice this is not something that takes a long time to solve. 175 divided by 360, 49. We'll round it to hundredths, 0.49. This is approximate. So 49%. So almost a 50% chance. Almost a 1 and 2%. I didn't draw this to scale as it is in the book. A 49% chance of hitting either purple or yellow. Okay, so angle measurements, and that's how you will do those. And again, it's always out of 360, and you get solving it. It's not going to take very long. You're definitely welcome to use your calculator. Okay, number 4, general area. This is the drawing from example 4, and it says, are you more likely to hit the trapezoid or the circle? Are you more likely to hit the trapezoid or the circle? And let me just quickly get the circle's dimensions on there. Forgot to put it. The circle has a radius of 6. So we need to compare the probabilities of hitting the trapezoid versus hitting our circle here. So let's find the probability for each one. And again, that is a simple fraction calculation of the area of each shape over the total shape. So we'll do the trapezoid. Area of a trapezoid is 1/2. You add the two bases together times the height. Okay, so we're going to go 3 or 1/2 times 3 plus 12 times 10. So that's 15. 15 times 10 is 150. Half of 150 is 75. So the area of the trapezoid is 75. And it's meters squared. Okay. So that's our numerator. That's what we're aiming for. Total possible area is this big rectangle, 45 by 20. So that's going to be base times height. So the area of the large rectangle is base times height, 45 times 20. And so that means it is 900. Your total sample space is 900 meters squared. So now we just set up our fraction. So we go 75 over, I'm not going to do it there, I'm going to run out of space. 75 over 900 equals, calculate that. Oh, there it is, 0.08 or 8%. So you have an 8% chance of hitting the trapezoid. So now we need to compare that to the circle to know which is more likely. So let's do the circle now. The circle, area of a circle is, very good, pi r squared. Our r is 6, so that is pi 6 squared, or 36 pi. And I can quickly, let's calculate that. 36 times 3.14. The approximation is okay, though if you have the pi key on your calculator, go for it. So 113.04. So this area is 113.04. Now, I'm going to go ahead and calculate the percent, but I can see already which one's more likely. I'll just probably need the number to prove my point, but we can see the circle actually has a greater area than the trapezoid, and so it's going to be more likely. But there's my new area, because I already know my total. So this fraction would be 113.04 over 900. And let's go ahead and calculate that. 113.04 divided by 900. So I get I'm going to say 0.13. Okay, this comes out to 0.13 or 13%. And so we can see I've got a slightly more likely, higher probability of hitting. It is the circle is more likely. Okay, so notice that was just an advanced question, but we're taking the area. They could have asked the probability of just the trapezoid or just the circle. This one made you calculate both and compare the two. Okay, so those are the three types, three types that you'll be looking for. Area, let's get these lined up. Okay, length, angle measurement, or area. And it's always just the selected over the total possible. Okay, good luck. We'll see you with the practice, with the classwork.